So what we're going to do today, we're going to actually do an example. This is not the example from your suggested exercises, but you should still do the example from your suggested exercises, because the example from your suggested exercises is like the most trivial example, but it still like appears everywhere. So that's fine. Okay, so let's do a little bit of review for a second. And I will kind of, it's going to be a sketch of a review. So review. Review of what? What did we learn last time? We learned the postulates. Or was that before? Yeah, last time was postulates. So the postulates, which ones did we list? We listed, so the first one was what? Do people remember?
Yes.
What was it?
Okay, wait. A state, in an isolated system, a state is completely described by a vector in a Hilbert space.
Yes. Well, yes. So the state of an isolated system is described by a vector in some complete inner product space, which is a Hilbert space. Which is a Hilbert space. Okay, that's one. That's two. Two was what? What was two? There were, yeah, subpoints. So yeah. Yeah, so to every physical measurement have associated observable, which is a self-adjoint operator on the Hilbert space. Okay, and what did we have? We had that part A was the eigenvalues. The eigenvalues of observable, what did they tell us?
The possible measurements.
Yes, so the possible outcomes of the physical measurement, so possible outcomes of physical measurement. So, and then part B was if we are in state psi, well, we, by we I mean the system, system is in state psi, such that psi has norm 1, then probability to measure lambda is given by, so probability of lambda is equal to the sum of the inner product between, what was it? VI, no. Yeah, it doesn't matter. Between VI, so let's do psi VI, yeah, all squared, right? And we're summing over the i's, so where VI is what? Yes, so VI is an eigenvector with eigenvalue lambda, and also you have the norm of vi is equal to 1. So essentially, if you have this measurement, you have this observable, right? It has, since it's self-adjoint, on a nice enough Hilbert space, not all of them, but on a nice enough Hilbert space, it will form a basis of eigenvectors, right? Because that's what we kind of proved in the spectral theorem. So at least in the finite dimensional case, you know for sure that you're going to have a basis of eigenvectors. So what you can do is you can look at, if you are seeing, okay, what is the probability that if I'm in some state, what is the probability that I can actually measure lambda, then you look at all the eigenvectors with eigenvalue lambda, inner product them with phi, square that, sum over, and that gives you the probability of getting lambda. So why does this why is this always less than 1? Well, because all of these VIs have to be orthogonal, right? And if you take all the VIs, you can then extend them to a basis of the whole space, right? Because you know they have to be linearly independent, so you can extend them to the basis of the whole space. And then you know that these have to be kind of psi inner product VI has to be the coefficient in front of psi, so in front of VI if you expand psi in terms of the VIs. So if you take the VIs, turn them in, and then extend them to a basis, right? Then psi inner product VI, we showed that that has to be the coefficient in front of VI if you expand psi in terms of VI. Remember? But that's only because the VI are orthonormal, right? Why is that the case? Because the observable is self-adjoint, and if you in one of the problem sets you showed, suggested exercises, you showed that if you have a self-adjoint operator and it has two eigenvectors, then they have to be orthogonal to each other. You showed that in one of them. Two distinct eigenvectors that aren't just scalar multiples of each other. Okay? Good. Okay, and then there was a third thing where if lambda is actually measured, then the state collapses. So if lambda then state collapses onto the eigensubspace. And then you also want to normalize it. So the formula is psi. Can people even see this? You can't. Psi gets sent to, okay, now you can see. Psi gets sent to psi vi sum over I divided by the norm, by its own norm. So where vi are as above here. Okay, good. Yes. So this is just a review of what we did before. Okay. So now, once again, I could do the really simple example that we did, that was on the problem set. But I won't, because I won't. And so instead we're going to do a slightly more complicated example, which you will see in your first year course. So the really trivial example you don't see in your first year course, but the more complicated example you do see in your first year course. So we're going to look at a particle in a box. And in a box. Okay, so if I want to define some theory of quantum mechanics according to these postulates, so once again, these are not all the postulates. There's a few more, but we will talk about them later, or maybe not. The main postulate that we're missing the Schrodinger equation, right? Because everything I told you kind of at one instant in time. I didn't tell you how this will all evolve in time, right? But okay, that's something that we will talk about later, maybe. Okay, so the particle in a box. So if I have the postulates like this, if I want to tell you a theory of quantum mechanics, what do I need to tell you? What's something I need to specify?
Theory of quantum mechanics.
Well, if I want to give you describe a quantum mechanical system, what do I need to yes?
Number of spatial dimensions if we're doing over time.
No, I'm following these postulates. What do I need to give?
Possible states. Is it possible to
Yeah, so I need to give you a Hilbert space, and maybe I need to give you an observable. The fun part is in physics, often you start with an observable and then figure out what the state space should be. But okay, for now we'll look at this formulaic approach, but this is not actually how people usually do it, and this is not always, you don't always exactly know what your Hilbert space is. But okay, that's a separate point that we will not talk about too much. But first I'll give you the following Hilbert space. I'll give you L2, capital L2, which is functions from R to C, such that, actually, I'll do even simpler. We'll do even simpler. Okay, these functions won't be from R to C. These functions will be from, say, 0 to L. So they're defined on the interval 0 to L, and they go into C. And I want these functions such as the integral from 0 to L of f, magnitude of f, absolute value of f squared, is finite. Okay? This is the space. So all functions that are defined on the interval 0 to L, such that if you take their magnitude squared, you integrate that, I guess dx, so f of x dx, you get some finite number. Okay? These are going to be our states. Okay? Good. Now, now we're going to do what? Now I need to tell you what the inner product is, right? Because so far I've just defined a vector space for you. Because it's obvious that this is a vector space because it's in functions. Of course, you can add functions, subtract them. Now I need to give you an inner product. The inner product between f and g is going to be the integral from 0 to L of f of x times g bar of x dx. Okay. So I'm just taking a function, multiplying by the other function, and then integrating them. The bar is important, that's the complex conjugate. Why do we need the complex conjugate? Remember that you wanted to have skew linearity in the second slot. So if you pull out a lambda out of here, it would come out as a lambda bar outside, so you need to have a bar over here. Yes?
Okay, so the first thing is just the eigenvector space, or what is it?
This is a Hilbert. This is the Hilbert space.
Okay,
So
yeah.
some function in here is somehow, so if I have I'm telling you that we have some system which I'm calling particle in a box, and then the state of this particle inside some box will be somehow fully described by a function from the interval to C.
Okay.
And I've not told you how we will do this yet, but I'm telling you that this function will somehow do it. And these functions are called wave functions often. Or at least you often refer to something like this as a wave function. Okay? We will see why in a moment. Okay. Actually, the other thing, I will actually add one more condition. I forgot. Since it's a particle in a box, we will also add the condition that psi of 0 equals, over f of 0. F of 0 equals f at L equals 0. So we have functions that are kind of 0 at the edges of their domain of definition. Why? Because look, I want to have a particle in a box, meaning that I don't want my particle to be able to leave the box in some sense. So for some reason this function has to be 0. Okay, we will see why in a moment. Okay. Now I better give you some observables. Do you agree? Right? Okay. So I'll give you I'll give you 3 observables. We'll start. Let's see if I can remember them though. This is going to be tough because I don't remember. So observable number 1, P, The observable number 1 is going to be P. This is a operator. So an observable has to be a self-adjoint operator, right? So P, so observables. Yes, okay, actually one thing that you need to double check, one thing that's not clear here is, look, here I assume that the square of the function, the function squared is the integral of this is less than infinity, right? It's finite and well-defined. However, I didn't tell you explicitly that the integral of f times g has to be less than infinity. Turns out, if your functions are square integrable, then the product of two square integrable functions is, the integral of the product of two square integrable functions is finite, right? So, turns out that if f has this property and g has this property, then this is finite. But this is something that you need to show, and it requires some amount of effort. I will not be putting in this effort. You can believe me that, of course, this is finite. Yes? Of course this is finite. Say it with me, class. Okay. Surely this works. Okay. So observables. We're going to define the observable P. Observable P is from where to where? So it's from L2 to L2. Right? Observable P is equal to minus I partial x. Is that right? There's a minus here, so that's good. So, actually, I guess it doesn't matter. Okay. So how is this an operator? Right? What does this notation mean? This notation simply means that it takes it takes some function psi, so it takes a function psi of x, and sends it to minus I times the derivative of psi of x. Okay? So maybe I also should say that these functions should be differentiable, but maybe we can like skip over that part as well. Because maybe if your function isn't differentiable, maybe you can still somehow differentiate. Or say something that like kind of makes sense and not care about it too much. So okay. So does this make sense as an operator? Yes? Takes a function, sends it to its derivative times some complex number. Very good. And okay, you would also need to double check that that this is indeed an L2 function, meaning that if this integral is finite, then this integral if this integral is finite with psi instead of f, then the integral of this thing in there would also be finite. But you can kind of do that maybe by integration by parts or something. And I don't remember how exactly to prove it, but I think you can just do it the integration by parts and use some inequalities and it works. Okay? So this is going, I called it P, so what will this observable be associated with? Pardon? Well, yeah, but which measurement? What kind of measurement? What kind of measurement is P? Momentum, yes. So this observable is going to be the momentum observable. Okay?
How do you check this
You good point. So you plug it into here. So what was self-adjoint? Self-adjoint was V AU is equal to AV U, right? That's what self-adjoint meant, right?
Yeah, I was thinking of.
So now all you have to do is check that if I put a partial on this guy, then this integral will be the same as putting the partial on this guy. How do we check this? You will use integration by parts, and you will also need this fact. So you can. So for now, since I'm trying to get through this really fast, I will simply put this on the next set of suggested exercises where you will. Actually, let's do it together. Let's do it together. So let's check that this is self-adjoint. Okay. Let's check that this is self-adjoint. How do we check that this is self-adjoint? How do we check that this is self-adjoint? So I want to do what? I want to have, say I have some functions psi, I have some function phi, I want to check that p of phi is equal to p of psi of phi, right? This is what I want to show. Do you agree? Okay. So let's just expand this side and then show that it's equal to that side. So how am I going to do this? I'm going to do, so this is equal to what? This is equal to the integral of psi times the bar of minus I partial x of phi. Do you agree? So I just plug stuff in. So far, so good. Now, this minus I, right, since it's inside of a bar, I can move it out, put the bar over, it becomes I, because the conjugate of minus I is I. Right? You have A plus BI, conjugate is A minus BI. Here the A is 0, so conjugate of I is minus I. Okay, good. So I can bring this out. So this is going to be just I phi. And then, so we have the partial derivative of phi, right? But now I can do integration by parts. Do you agree? Do people remember how integration by parts works?
Yep.
Vaguely? Okay, so integration by parts would then tell me that I have I psi of x times phi of x from 0 to L. So evaluated at the bounds of from at 0 and L. So I plug L into this and then subtract plugging in 0 into this, right? And then I'm going to have minus the integral. So I had the I left over, right? I, and then I'll now put the derivative on the other thing, which was the psi, times phi bar. Whoops, my bad, there has to be a bar over this phi because I forgot. I forgot the bar. Do you agree? There was a bar here, bar over this phi, I forgot about it. Because there was a bar over this phi here. The partial derivative does not get affected by the bar because the partial derivative is real, x is real. Right? So if you just explicitly look at the limit, then the t goes to 0, that part doesn't get affected. I can factor out or whatever. Okay. So people agree with how we got to here, right? Okay. But this psi of x times phi of x from 0 to L, what does this evaluate to? 0. Why? Because by assumption, I said that my wave function should go to 0 on the boundary. So now I get this is what? I get that this is the integral of minus I partial x psi times phi bar, which is exactly p of psi inner product with phi. Okay, so we proved this. You agree? So that's why you needed the minus here, I guess. I mean, you didn't really need it. You could have done it without the minus, it would have still been fine. But that's why you kind of need the I here, so that when you do the integration by parts, you get a minus sign, but then the minus sign cancels out from the minus sign that you pick up from the I. So that's why you need the I. Okay. Does this make sense? Yes. So now, we're going to do what? We're going to try and figure out what are the possible momentum states. Okay? What are the possible momentum measurements I can do? Is that fine? Right? So we did postulate 1, I told you what the Hilbert space is. Then now I gave you an observable, and now let's figure out what the eigenvalues of the observable are. Okay? Is that fine? So, okay. To find out the eigenvalues of the observable, so I need to solve the eigenvalue equation. What's the eigenvalue equation? Or if a state is an eigenvector of p, what does it have to satisfy? It has to satisfy it. Okay, good. But what was p of psi? P was minus I partial x of psi is equal to lambda psi. So we're searching for lambdas and psis such that this equation makes sense and is true. Do you agree? That's what we're searching for. Do people know how to solve this?
Yeah?
Have you guys learned about the exponential function?
Yeah, I think you have.
Okay. So now suppose I wrote this like this. It's equal to I lambda psi. Okay. 1 over I is minus I. Okay. So I just rewrote this equation. It's okay. How do I solve this now? What's the solution to this equation?
It's C multiplied by e to the power of I lambda x.
So psi is C multiplied by e to the I lambda x. Do you agree?
Or that with the constant.
So let's check that this in fact solves this by just taking the derivative of this and multiplying by minus I, right? So P of psi equals minus I derivative of x of e to the I lambda x, right? So what's the derivative of e to the kx? It's k e to the kx, right? You just bring down one factor of k. So this is minus I times I lambda times e to the I lambda x. Okay, and there was a c that I lost. C. Okay. This is a bracket, this is a c. So I have I times I gives me minus 1. Minus 1. The minus cancels the thing. So I'm just left with lambda c e to the I lambda x, which is equal to lambda psi. So people believe now that this is indeed the eigenstate that we want? Okay? So what does this tell us? What does this tell us? This tells us that if we want if we have some function that looks like this with some lambda, then we get that what was I saying?
Oh, it's an eigenstate of
Yes. Yes, so this is an eigenstate of the operator, and that lambda is a possible momentum that we can measure. Somewhere here, it should be clearly encoded that lambda has to be real, right? Because we can only have real eigenvalues. Why does that follow? I'm not immediately seeing why lambda necessarily has to be real. Suppose lambda was complex.
Yeah,
It's
we have
because of the
because
boundary
they have
conditions.
complex.
It's because of the boundary conditions, right? Yes. So this is true. This is because of the boundary conditions. If lambda was complex, then you wouldn't be able to satisfy these boundary conditions. I will not entirely explain why. But because once again, I want to finish in the next 12 minutes.
Okay.
No. Good. So this makes sense, yes? Maybe. It's okay. You agree. So you agree that this is some function in L2. Hopefully the integral of this converges. But it should, because you know that this looks like a continuous function, right? Because it's e to the something. Surely it's continuous. And continuous functions on an interval are always integrable, and then so products of two continuous functions on an interval should also be integrable. That's something you should know from 157 somewhere, or you will know from 157 eventually, if you don't already. Okay, good. So now the question is: so what are the eigenvalues then? What are the eigenvalues? The main question: what are the eigenvalues of P? What are the eigenvalues of P? What are all the possible eigenvalues of P?
Oh,
Pardon?
all the measurable values we can see.
No, sure, but I gave you this is, at this point, this is a math question, because I told you what P is, and I'm trying to find what the eigenvalues of P are to say that this is all that the momentum can be. So what should the, in theory, what kind of momentum should I be able to have? All real numbers. Okay, true. So that is indeed the case, right? We just showed that if lambda is a real number, then I get a wave function that works and solves the eigenvalue equation, right? So we just showed that all the eigenvalues are of this form, have to be real numbers.
Why exactly not complex?
So, good question. I haven't explained this well enough, but the point is, if this was a complex number, then you wouldn't be able to have this satisfied. You know what? Why not? Let's show it. Let's show it. I'll just talk a bit less about something else. Or maybe I won't. Maybe I'll still talk about it more and you'll just fail your problem set. That's okay. That's okay with me. You fail 157, so you can like ace 247 and 256 next year. Well, 247 this year. 256 next year. Okay. So good question. How do you guys know the Taylor series of e to the x or not yet? Yes, in principle. Maybe in 157 you've talked
There was
about
a
it.
problem, but I did not do it. So in principle.
Okay. In that case, you just kind of wait for the final result. So we know that e to the kx, right, is equal to
I know this one.
1 plus kx plus kx all squared over 2 factorial plus plus kx to the n over n factorial, and then so on and so forth. Do you agree? Now suppose instead of k, I plug in I lambda. Okay? K equals to I lambda now. I just do I can always do this, right? I can always set k to be I lambda, because I can always say lambda is equal to k over I, right? I can always do this kind of relabeling. Yes? You agree with that?
Equals lambda over I.
I'm saying let lambda be such a number such that k equals to I times lambda. Right? You agree I can always do this?
Yeah.
Okay, good. So now I'll do I lambda x, right? But then this is plus, okay, I have I squared here, right? I have I lambda x all squared.
Oh, that's.
But then the I squared turns into a minus. Do you agree?
Oh, so it's just sine and
So
cosine.
it's a minus. Don't spoil the answer for others.
I prefer the.
Over 2 factorial, right? Okay. Then plus the next one is going to be not plus, you're still going to have a minus, but it's going to be minus I lambda x cubed over 3 factorial. Why? Because here you have I to the 3, but I to the 3 is I squared times I. I squared is minus 1, so you just have a minus I left over. Okay. And then you'll have plus lambda x to the 4 over 4 factorial. Okay, and so on and so forth. So you'll see that each time you're going to have like an alternating minus sign. So the odd powers are going to have an I in front of them, and they're going to alternate sign. And the even powers will also alternate sign, but they won't have a minus sign in front of them. Do you agree?
What do you mean they're gonna alternate
So-
sign? Because you have a minus and then plus.
No. So if I look at only the even terms, it's going to be plus 1, minus, plus, minus. If I like skip in 2s. Here it's plus, minus, and it's going to also skip in 2s, right? Because every time you like skip in 2s, that means you multiplied by I squared, right? Because you're going to have I lambda x to the 2, like n plus 2, right? That means you multiply by I squared, means you added up a 1. So now I can look at the even terms, so terms with even powers, and then the odd powers, and sum them up separately. Do you agree? So I'm going to have the sum of what? I'm going to have the sum of lambda x to the, let's do the even powers first, 2n over 2n factorial. And this is going to be minus 1 to the n, because the minus 1's gonna, the first term is gonna be plus 1, the next term is gonna have a minus, okay, because we just saw this, right? So this is from 0 to infinity, and plus, n equals 0 to infinity, the odd terms, but the odd terms are gonna have an I in front of them, so I, minus 1 to the n, and I want lambda x to the 2n plus 1, and I want the first term to have, yeah, that's good, and 2n plus 1 factorial. Okay. Some of you may recognize that this is the Taylor series for cosine, and this is the Taylor series for sine. If you don't recognize that, well, look here. It's like one. It's remember that sine x is equal to x, right? So, hey, that's the first linear term. So surely, okay. So this is sine kx. Oh no, what am I saying? Not sine. This is cosine kx. Cosine lambda x plus I sine lambda x. Okay? And so now, yes. Okay?
I have a question.
Yes.
Are you pretending that the error term doesn't exist? Or
What do you mean error term?
Like, isn't e to the k of x equal to all of that plus error term?
No. If you sum up all of this up to infinity, right? So I have dot 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 at the end. So I'm taking an infinite sum.
Okay.
And the infinite sum converges to exactly e to the whatever. That's what I'm saying. Okay. Do you agree? Okay. Now, if lambda is a real number, then we know how to compute this, right? If lambda is a real number, then you know what cos is and what sine is, and you can compute this. Do you agree? Okay. So now let's look at the. Okay. So now, then let's look at the following. Suppose I had e to the a plus bi x, right? Where this was, where x was a real number, a and b were real numbers. So this is overall by a complex number. Do you agree? So then what does this mean? This means that this has to be equal e to the a multiplied by e to the bix. Okay, ax. Sorry. Ax times e to the bix. Okay. I haven't proven this property yet, but you know, the fact that for complex numbers it also factors nicely like this, but it does, because you know you would expect this to work. Yes, that makes sense how we got from here to here. So then now we can use our magic formula. Have e to the ax multiplied by what? By cos kx plus cos bx plus I sine bx, right? Right? Yes. Oh, wait, no, but to have the boundary conditions, I need to take a linear combination. Right? At the end of the day, I still need to take a linear combination.
Then why? Because your differential is only for order. So you don't have a second eigen.
No, but if I plug in x equals 0, I will always get 1.
Oh, yeah.
Yeah, so I do need to take a linear combination of them. Okay.
I think we've seen this in like physics 152.
Yes.
They have seen it. So
Yes.
This is the what's it called?
Yes.
The damped harmonic oscillator.
Yes.
It's in a problem set.
Yes, that's fine. Okay. My bad. I'm messing up. So these are not.
So like if you draw a damped harmonic oscillator, you can never get to the zero
Mhm.
at the same time.
Okay. So I'll clarify this bit, and then we will back to it. So, what did I want? Right, I wanted the.
Wait, it's not right.
Yeah, that looks right. I wanted the boundary conditions such that way. I wanted this to be
No, you can still have a zero.
by having what?
You just have the oscillating part become zero, so the exponential part doesn't matter.
No, but if I plug in x equals 0 here, I just get 1. Always.
You need a linear combination.
Yeah. Okay, to make this simpler, I will just simply change our thing to be defined not from 0 to L, but from minus L to L. Okay? And if we do that, then it works. Or it should work.
Is that how you normally do it in the first stage calculation?
I think you will do minus. For you guys, you just write, you wouldn't do the complex exponentials. You guys would just write sine and cos. And then you just get that, the solution to. Oh, it's not exactly what you do. You wouldn't really be talking about the momentum operator too much in first year, to begin with. So in first year, what you would talk about, if I had more time, you'd talk about the Hamiltonian, which is the energy operator. And so, so I will, okay. So the point is that, so the eigenstates that we want either have to be some linear combination of these e to the, of these complex exponentials, and I showed you what they are, and okay, I want to finish in the next 5 minutes, because you guys have to go. So this is not entirely clear, but then what will hopefully be more clear. Okay, I will erase the postulates, and then we'll do the eigenstates of the energy Hamiltonian, and then hopefully, and then we'll be done. So this will be very quick. I will erase the postulates. Wait, why do I have two cloths? I'm so confused. Oh wait, no, this one's not mine. And this one's mine. Okay. So I'm going to define the Hamiltonian to be minus p squared or something
No, it's
over
just,
2?
It's just p squared.
Just p squared, right. So p squared over 2. Okay? Why is this the obvious thing to take? Why is this the obvious thing to do?
Oh, it looks like kinetic energy.
Yeah, it looks like kinetic energy, but like I set mass to 1, right?
Yeah.
Kinetic energy is a p squared over 2m. Here I just set mass to 1. Okay, so I mean, this makes sense why you would want to do this. Also, in general, taking kind of the derivative of something to be the momentum also makes sense, because velocity is like the derivative, right? Right, to get the velocity, you take a derivative in x. So it kind of makes sense to have y momentum as I partial x. Okay? Good. So h is going to be p squared over 2. Do you agree? So now we're going to search for the eigenvalues of this thing. Right? So question, what are the eigenvalues? And then these eigenvalues, once we figure out what they are, they will let us understand what this has to all be. Okay? What the energies could be. Sorry, what the energies could be. Okay. So we have to solve just the same thing as before. Has to equal to lambda psi. So we have to see what lambdas make this equation solvable in general with the right boundary conditions, and what the psi associated would be. Yes? the question?
I think one of the eigenvalues is it's like similar to what we had before, so it's about
Not quite. So, okay. So this is what the equation that we're trying to solve is. So it's minus 1/2 times the derivatives, you do the derivative twice, of psi is equal to lambda psi. Do you agree? Okay. Maybe this half, I'll move this half as a 2 to here, so this is okay. Minus. You guys surely know how to solve this one. What's this one? Yes.
I think it should be e to the power.
So even simpler. Sine and cos, correct. So this is solved. Psi has to be so a sine. Yeah, what were you saying?
Wait, no, just
Sine
lambda
of-
sine. 2 lambda sine x.
It should be square root of lambda. So
Okay.
I'm assuming lambda is positive here. Actually, I should say lambda is positive. If lambda is positive, because I want positive energies for whatever reason, I'll have square root of lambda, right? Square root of lambda. Maybe I have a root 2 here as well. Maybe I don't need the over 2, right? Why did I need the over 2? Okay. Why did I need the over 2? Okay, that's fine. Lambda x plus b cosine. Actually, I'm gonna switch this back from 0 to L. So ignore that discussion. Sorry, there's a square root here. Okay? So I'm saying that my energy eigenstates have to be of this form. Has to be some combination of sine and cosine, right? Okay. So now I go back to this boundary condition that I was talking about with 0. I want psi of 0 to be equal to 0, right? If I plug in 0 here, this sign is 0, right? So this term is 0. But this term is always 1, right? So this means b has to be 0. Do you agree? Meaning that my energy eigenstate has to just be a sine square root 2 lambda x. Okay? Now I'm going to do the second boundary condition, that psi of L has to be 0. Do you agree? This means that square root 2 lambda times L has to be equal to 2 pi times some integer.
Isn't it just pi?
Hmm?
Just pi n? Because
Oh, right, pi n, my bad. You're right. Not, yeah, pi n.
Where did you get that from?
So if I want sine of something to be 0, then that something has to be pi times an integer. Right? Because sine is only 0 if you plug in pi times n. Right? So if I want psi of L to be 0, I want 2 lambda times L to be equal to pi n. Do you agree? But what does this tell me? This tells me that lambda has to be equal to pi n over L all squared times a 2. Maybe I shouldn't have this 2 at all, but okay, that's fine. I set it up this way, so we'll stick with it. Maybe it should just be p squared, and that's fine. Okay? Do you agree? So now we see that if my part, so now we see what lambda has to be, and we see what psi has to be in terms of this lambda. So can I rewrite this somehow? Oh wait, sorry. This has to be 1 over 2. Yes? Yeah, there we go. That makes sense. Sorry, I did the algebra wrong. Do people see how we got from this step to this step?
Yes.
So we have kind of, this is important, this is important. So now let's plug in this lambda into here. Do you agree? So I get that my psi has to equal to some normalization constant, 2 sine. So if I multiply 2 lambda by this lambda, I get what? I get pi n over L, because I take the square root, times x. Okay, so this is what my wave functions have to look like. Do you agree? Yes? Okay. So what is the significance of this? Let's look at this for a little bit, and then we'll talk about it more next time.
The wave.
Well, okay, sure. That's fine. That's a wave.
The wave function.
Well, I mean, I said that let's call these wave functions from the beginning. So the fact that it's a wave is, okay, maybe that's interesting. Not so much to me at the moment. What's really interesting? What are the possible energies? What were the possible energy? Which number here was the possible energy? Which of these letters tells me the possible energy I could measure?
N.
No. Lambda, yes. By initial assumption, by saying, hey, this is some observable, has to be lambda. Right? So actually, one thing we didn't check that this is self-adjoint. But it is. Don't worry about it. So, yeah, lambda are the possible eigenvalues. What did we say? N has to be what? N has to be an integer. Do you agree? But lambda has to be, something in terms of n. This means that all of the energies are indexed by some integers. Do you agree with that? Yes?
I guess so, because it's an integer times a constant.
Yeah, because it's pi over L. Yeah, exactly. So we showed that lambda has to be of this form where n is an integer. So this means my possible energies are not continuous. The energies that I could possibly be have to be discrete and are indexed by some integer n. So now I will introduce En to be kind of the lambda associated with this energy level. So this is going to be pi n over L squared. Okay. So these are the allowed energies, right? And so the allowed energies are somehow discretized. Do you agree? Yeah. So this is surprising. All of a sudden, we did this kind of approach, and we got that for our system that I called a particle in a box. We get that if you constrain a particle into a box, into like it's a one-dimensional particle, so you have some interval from 0 to L, and your particle it can be inside of this interval. And I'm telling you that for some reason this particle is described by this thing called a wave function, which is just some function that is square integrable. And I'm telling you that, okay, the Hamiltonian has to be this thing for whatever reason. And then we showed that, okay, the energy, so the eigenvalues of the Hamiltonian, so the Hamiltonian is the energy observable. So the possible energies that we could measure on this particle, all of a sudden, we get that they're quantized. So the spectrum is not continuous. The energies that we could measure, it's not, I can't get like 1, 0.1, 1.001, I can't get any number I want. I can only get these specific numbers which are indexed by the integers, right? Yes?
Wait, why is the Hamiltonian's eigenvalues the energy levels?
So I'm telling you that let's call the observable associated to measuring energy the Hamiltonian. So I'm telling you, this is the observable associated to measuring energy. I'm telling you this.
Okay.
And you're believing.
So given.
Yeah, it's given. It's given. Yes. There is actual physical motivation for why this should all be the case and why this should all work that you can do, but I'm not doing it right now because I want to kind of talk about the postulates for now. Okay. So you get that this has to be the energy levels of our system. Yes. And you can notice that this is almost like a momentum. This is almost like the momentum eigenstate of our system. but not quite. This is a linear combination of momentum eigenstates. Actually, yeah, you need to like do stuff with the momentum. Maybe we'll talk about it. I'll put it on a suggested exercise, and then we'll talk about it again later. But so I guess for the people on video, I'm like really rushing today because they have a problem set due, so I want them to do the problem set instead of this. But this is kind of the major takeaway, that you can have this particle in a box system where the states are these L2 functions, and the Hamiltonian is this p squared over 2 thing, and that if you were to look at the eigenvalues of this Hamiltonian and look at the eigenstates of this Hamiltonian, so the eigenvectors, if you were to look at them very carefully, you will realize that the allowed energies in the system are actually quantized and not continuous, right? And okay, so you also get a kind of orthonormal basis of this, and this is something you can check. One thing that would be interesting to check is see, okay, if I take a sine pi n over L times x multiplied by another sine pi m over L times x, where n and m are different integers, and then I do the integral from there, from the inner product, then you should get 0. Which is exactly to show that the states are orthogonal. So you want to show, and it is possible to show, that sine p n over
It's cropped up in 157 and then in 247 and then now here in that order.
pm over Lx has to be equal to 0. So why is this surely true? Because, well, so one way to do it is just to compute it explicitly, do the integral, and then you get that it's 0. The alternative way is to realize, well, we can check that h has to be Hermitian, right? Why? Because it's p squared. Okay, I'll not talk about it. Suppose h is Hermitian, right? And you hope that the spectral theorem holds for this L2, because L2 is infinite dimensional in principle, right? We also need to show that it's complete, but it's complete, trust me. So if you knew that L2 has a spectral theorem that kind of works on it for h, then you'd see, well, this is an eigenfunction, this is an eigenfunction, this is an eigenfunction, and they have different eigenvalues, so they have to be orthogonal, because they're different eigenfunctions of a Hermitian operator, the self-adjoint operator. So that's one way to kind of make a heuristic argument that it's 0. But, well, actually, no, you should be able to just prove that in general but you'd need to then prove that this is a Hilbert space or something, which is maybe a little more tricky. Yes, but this works. Okay. We will go over this in more depth next time. Yes, and prepare for the presentation.